Okay, you guys, we're going to talk a little bit about Lewis dot structures. I encourage you to take a peek at this before you start on your Lewis dot structures POGIL, but I'm sure you'll be able to figure it out either way. So the first question we want to answer is, what are atomic Lewis structures? A Lewis dot structure is a diagram representing the valence electrons in atoms. Valence electrons are the part of the atom that does the chemistry, so it does all the interesting stuff that we care about. So instead of drawing out a full Bohr model, we just skip it and we just write the atomic symbol and draw a dot to represent the valence electron. It's way faster, it requires less counting, and it ends up being pretty elegant. So that's kind of nice. Typically, we use it to depict covalent bonds. So a nonmetal bonded to a nonmetal, and we use it to depict molecules. Like I just said, consists of an atomic symbol with the valence electrons around it. In potassium's case, there's only one valence electron, so there's just one dot. How to draw a Lewis structure for a single atom. It's easier than it perhaps sounds. So the steps to follow are these. Determine the number of valence electrons. You can look at your periodic table to do that. Or you could draw a Bohr model, but that's a lot of work. You will then write the chemical symbol of the atom to represent the nucleus. So take the symbol from the periodic table. You will draw a dot for each of the valence electrons, and then you're done. Some rules that apply to this are the following. The maximum number of dots you can have is 8. You will never have more than 8 dots around your atom or around your atomic symbol. And if you have a dot all by itself, like the potassium on the previous slide, we call that an unpaired electron. If there's 2, it's a pair. If it's 1 by itself, it's unpaired. So here's some examples of Bohr models so that we don't have to draw them all out while we're looking at practicing our dot structures. And you can see that the outermost circle, the lightest shaded circle, that's the valence. All right. So like lithium has 1 valence electron because it has 1 dot on the outside circle. Beryllium has 2 dots, so it has 2 valence electrons, and so on and so forth. So if I was going to draw some Lewis dot structures for these elements, the first thing I would do is find the Bohr model. I just copy pasted them onto this slide so that we wouldn't have to flip back and forth. So nitrogen, its Bohr model has 5 valence electrons in the outermost circle. And so I would just write a capital N for nitrogen, and I would put 5 dots around it. And so you can see I put 2 together and then I put 1 on each side. But if you wanted to put 2 together on one side and 2 together on the other side and then put 1 by itself, it would be fine. Phosphorus also has 5 valence electrons on the outside. Even though it has more electrons on the inside, we don't care. We only care about the outside ones. So it has 5, so we can put 5 dots around it as well. Magnesium has 2 dots on the outside, so we would write Mg for magnesium and put 2 dots. And then calcium has 2 electrons in its outside also, even though it has more on the inside. It has 2 on the outside as well. And so we would write Ca for calcium, and we would just draw the 2 dots that go on the outside. What I'd like you to do now is open the student response sheet that goes with this presentation, and I want you to do this practice. There's a table filled out for you. You can use the picture of the Bohr models 2 slides ago, and then you can figure out how many valence electrons and click and drag some dots to make your Lewis dot structure. Once you've done that, compare to this key. So aluminum should have 3 valence electrons, so we would put 3 dots around its symbol Al. Fluorine is capital F. It has 7 electrons in its outermost energy level, so we would do 1, 2, 3, 4, 5, 6, and then the 7th. Sulfur has 6 valence electrons, so we would do 1, 2, 3, 4, 5, 6. Sodium only has 1 little valence electron, and so we just write Na, the symbol for sodium, and then a dot. The reason we like Lewis structures is because they allow us to make 2-dimensional pictures of molecules, which, if you're a chemist, is actually super handy. So, to do this, we need to think about how do we read a chemical formula. So let's look at an example we know and love, which is water. There's the chemical formula for water, H2O. On your student response sheet, please answer the following. How many different elements are present in this molecule, and what are they? How many total atoms of each element are present? What kind of bond do these elements form, ionic, covalent, or metallic? And what happens to the electrons in this kind of bond? Are they shared or transferred? All right, so in this molecule, there are 2 different elements, and the elements are hydrogen and oxygen. There are 2 hydrogen because it says H2, and that little 2 goes with the letter before it, and there's 1 oxygen. Both of these are nonmetals, and so they're going to form a covalent bond. In a covalent bond, the electrons are shared. So now we want to relate the chemical formula to the Lewis dot structure. So here's the Lewis structure for water. What do you think the line between the atomic symbols might represent? And what type of bond holds the H's and the O together? So the line on here represents the shared electrons, or the bond, between the oxygen and hydrogen. And because they're a nonmetal, each has a covalent bond, which is the sharing of the electrons. So you would never see a line like this for an ionic bond, right? Because they're not sharing electrons. The line means oxygen and hydrogen are sharing electrons. Here's a little bit of a more complicated example. So we want to take the Lewis dot structure and then use that to find the chemical formula. How many different elements are present in this molecule, and what are they? How many total atoms of each are present? What do the lines between the atomic symbols represent? So, we have 3 different elements, hydrogen, carbon, and oxygen. There are 12 hydrogen, if you count them up, 6 carbon, and 6 oxygen. The lines between each of these symbols represent a shared bond and shared electrons. So here's the formula. Now that we know the number of each thing, we would write C6H12O6. You could put the letters in any order you wanted, right? You could do H12, C6O6, or O6, C6, H12. It doesn't really matter. Chemists have conventions for these things, but we don't care that much right now. Why do you think the line connecting the C to the oxygen on the right-hand side has 2 lines? So why is this 2 lines instead of 1 line? What could that mean? And then, again, what kind of bond are these elements all forming? And are they sharing or transferring their electrons? So when we have a double bond or a double line like this, it's called a double bond, and it means it's sharing 4 electrons instead of 2. which actually means it's a really, really strong bond because it's connected with two lines and not just one, so it's stronger. All of these bonds are covalent because all of these elements are nonmetals. So hydrogen to oxygen is covalent, oxygen to carbon is covalent, and hydrogen to carbon is covalent. This means that all of these electrons are being shared between the different elements. All right, that's all we really need to know about Lewis dot structures and chemical formulas and molecules. And this is going to help us later on in this unit when we start really digging in and looking at the water molecule, which is the most special covalently bonded molecule of all.